Okay students, the next topic, Unit 4, Hydrogen. Unit 4, Hydrogen. In this session, I am going to teach the position in periodic table. The hydrogen atom position in periodic table, in isotopes of hydrogen, explain ortho and para-hydrogen, then preparation of hydrogens. Preparation of hydrogen. So hydrogen is the simplest atom. Hydrogen is the simplest atom which contains one hydrogen and one electron and one proton. The hydrogen is the simplest atom which contains one proton and one electron. One proton and one electron. Right? So one proton present in the nucleus and one electron present in first orbit. One electron present in the first orbit is a valence orbit. First orbit and also valence orbit. Right? So in contrast with the other elements. Contrast with another element except the helium. Except the helium. The helium are also contained the first orbital, 2 electrons. Okay, so contrast with the other element except with the helium. Right? So the electron present in the near the nucleus. Near the nucleus, the more electrostatic force, the more electrostatic attractive force between the nucleus and electron is higher. The electrostatic attractive force between the nucleus and electron is more than other elements. More than other elements. Right? So, in our daily life, we come across, in our daily life, the maximum compound contains hydrogen. Maximum compound contains hydrogen. For example, water, H2O. Water contains hydrogen. 2 moles of hydrogen. Okay, 2 hydrogen atoms. Hydrogen molecules, H2O. And carbohydrate, glucose, C6, H12O6. So present in hydrogen in glucose. Glucose, fructose, sucrose, C12, H22O11, sucrose. Right? And polysaccharides, C6, H10, O5, N-times, like starch, cellulose, and etc. Right? So, in our daily life, we come across in our daily life, the maximum compound contains hydrogen. Example, water, carbohydrates, proteins, and etc. Right? So, the hydrogen contains only one unpaired electron. Hydrogen contains one unpaired electron. So hydrogen is a high reactive atom. Hydrogen is a high reactive atom. Okay, so presents in one unpaired electron. So unpaired electron easily react with the other elements. Okay, so hydrogen is a high reactive atom. High reactive atom exists in diatomic molecules. Okay, so H2, diatomic molecules H2 in gaseous state. However, the abundance of hydrogen gas in Earth atmosphere is very small. Very small. Right? The electronic configuration of hydrogen is 1s1. The electronic configuration of hydrogen is 1s1 is resembled with the alkali metal electronic configuration ns1. The valence electronic configuration of alkali metals ns1. For example, lithium 2s1, sodium 3s1. Okay, so potassium 4s1, cesium 5s1. Okay, so the lithium 2s1, sodium, potassium, rubidium, cesium. So 2s1, 3s1, 4s1, 5s1, 6s1. Okay, the general molecular formula NS1. NS1. Okay, so the electronic configuration of hydrogen is resembled with the alkali metal electronic configurations. Alkali metal electronic configuration. You right? So the similarity with the alkali metals. Are you right? So same electronic configuration. So similarity with the alkali metals. It forms unipositive ions. Hydrogen having one electron. So loss of one electron. The loss of one electron to attain H plus ions, proton. So it forms unipositive ions. H plus is a unipositive ions like alkali metals. Na plus, K plus, Cesium plus. Right? In sodium, Na plus, sodium, Na11. The size of atom is larger. The effective nuclear charge is less. The ionization energy is low. Ionization energy is low. So easily loss of one electron. Okay, so ionization energy to easily loss of one electron to attain noble gas electronic configuration. Okay, so sodium loss of one electron to reach neon electronic configuration. So potassium loss of one electron to reach easily in argon electronic configurations. Okay, so loss of one electron to attain more stable ions. So unipositive ions. It forms unipositive ions H plus like alkali metals. So similarity with the alkali metals. In second point, it forms halides. HCl, hydrogen chloride, HBr, hydrogen bromide. Okay, oxides, water, H2O, peroxide, H2O2, and sulfides, H2S, like alkali metals, sodium chloride, sodium bromide, sodium chloride, sodium bromide, sodium oxide, sodium peroxide, potassium chloride, potassium oxide, potassium peroxide, and etc. Right? The third similarity, it also acts as a reducing agent. Why act as a reducing agent? So alkali metals easily loss of one valence electron to reach noble gas electronic configuration. So the oxidation process is very simple. The Na, so easily loss of an electron, Na plus and B. Easily oxidized alkali metals, so act as a reducing agent. So hydrogen are also loss of an electron. It's an oxidizing process. Okay, this process act as a reducing agent. Okay, so easily give one electron to other ions. Are you right? Okay. However, okay, similarity, say dissimilarity. However, unlike alkali metals which has ionization energy range 377 to 520 kilojoule mole inverse. But in hydrogen ionization energy 1314 kilojoule mole inverse. Much higher than alkali metals. The hydrogen ionization energy is much higher than ionization energy of alkali metals. It's a dissimilarity. Okay, students. The hydrogens are also similarity with the halogens. Right? So all halogens easily accept one electron. The gain of one electron to reach noble gas electronic configuration. For example, fluorine F9 easily gain of one electron to reach F minus neon electronic configuration. neon electronic configuration. So 9 electron, 10 electron. Okay, so 9 electron, 10 electron. Okay, electron, next chlorine Cl. So gain of 1 electron. So electron in chlorine atom 17. So gain of 1 electron in chloride ion contain 18 electron. Okay, so reach argon electronic configuration. So more stable electronic configuration. Okay, this process is electron affinity. Electron affinity. So electron affinity is a exothermic process. Electron affinity is a exothermic process. In the periodic table, the high electron affinity contain group 17 groups. Halogen groups. Right? So a hydrogen are also gain of 1 electron to attain H minus. Hydride ion. Okay, resemble with halogen ions to reach the noble gas helium electronic configurations. So electron 2 electron to attain helium electronic configuration. However, the electron affinity of hydrogen is much lesser than halogens. For example, the hydrogen diatomic molecules, so of H2 plus gain of 1 electron to attain hydride ion. The del H value is equal to plus 36 kilocalorie mole inverse is a endothermic process. But the first electron affinity is exothermic process. But in hydrogen atom is a endothermic process. But in halogen gain of 1 electron easily to reach bromide ion. We are minus. Okay, so neon Grafton electronic configuration. The del H value is equal to minus, say exothermic process, minus 55 kilocalorie mole inverse. The symbol positive or negative indicate only endo or exothermic process. The value 55 is higher than 36. The minus plus symbol indicate only endothermic and exothermic process. The first electron affinity is exothermic process. Right? So the electron affinity value of hydrogen is much lesser than bromine or halogens. Right? So the hydride ions. From hydride ions tendency are also lower than halogens. Right? Okay, since the hydrogen similarity with alkali metals as well as halogens, it is difficult to find the correct position in the periodic table. However, the most of the compound hydrogen exists in H plus. So the reasonable place to give in the modern periodic table in group 1 along the alkali metals. So published in IUPAC. Okay. The next one is isotopes of hydrogen. The hydrogen has naturally occurring 3 isotopes. One is here protium. H1 protium. Okay, the second one is deuterium. H1 2. The third one is tritium. H1 3. Right? The first one is protium. The second one is deuterium. And third one is tritium. Okay, so the protium is the predominantly occurring isotopes. Hydrogen isotope. The predominantly occurring hydrogen isotopes. So occurring 99.985% in atmospheric hydrogen gas. Right? So the protium isotope does not contain neutron. That does not contain neutron isotope is a protium. One more question. Okay, so the only isotope does not contain neutron in the nucleus. Neutron present in the nucleus. You right? So the second hydrogen isotope, deuterium, is also called heavy hydrogen. It's also called heavy hydrogen. Okay, occur 0.015%. 0.015%. Right? The third isotope of hydrogen, tritium, is a isotopic radioactive isotopes. Right? The tritium, the third hydrogen isotope, tritium, is radioactive isotope. Radioactive isotope, so occur in traces. The one atom per 10 power 18 hydrogen atoms. So one atom per 10 power 18 hydrogen atoms. Right? So isotope of hydrogen. So in atmosphere, hydrogen gas exists H2, D2, right? So HT, 2 hydrogen atoms. Okay, one hydrogen atom, so one protium, another one is a deuterium. Okay, so deuterium molecules, proton and tritium. Okay, so tritium molecules, DT, deuterium and tritium. You right? So the naturally atmospheric gas, hydrogen gas exists H2, HD, D2, HT, TT, T2 and D3, right? Properties of hydrogen, deuterium and tritium molecules. The properties of hydrogen, deuterium and tritium molecules. Property, protium, deuterium and tritium. Okay, so the protium are also called normal hydrogen. The deuterium are also called heavy hydrogen. Tritium is a isotope, radioactive isotope. The atomic mass unit of protium 1.008 and deuterium 2.014 and tritium 3.016. The number of electron, proton and neutrons. Now protium H11 protiums. So one proton and one electron. So only the isotope does not contain neutron. Deuterium D12. So one proton, one electron and one neutron. In tritium T13. So one proton, one electron and two neutron. The nuclear stability. Protium is stable and deuterium are also stable, but tritium is a radioactive isotope. The half-life period 12.3 years. The half-life period means the time required to reduce the concentration of a radioactive isotopes to 1/2 of its initial value. half-life period is defined as the time required to reduce the concentration of a radioactive isotope to 1/2 of its initial value, 12.3 years. Molecular hydrogen H2, D2, T2. The abundance, the percentage of abundance in protium 99.985 and deuterium 0.015 and tritium is a radioactive isotope, so occur in traces approximately 10 power minus 16. The molecular mass, atomic mass unit 2.016 in protium, 4.028 in deuterium and 6.032 in tritium. Melting point of protium 13.96 Kelvin and deuterium 18.73 Kelvin and tritium 20.62 Kelvin. Boiling point of protium 20.3 Kelvin, deuterium 23.67 Kelvin and tritium 25.04 Kelvin. The internuclear distance between the protein, the internuclear distance H, the internuclear distance of protium 74.14 picometer, 74.14 picometer and deuterium deuterium internuclear distance 74.14 picometer and tritium the internuclear distance 74.14 picometer. Critical temperature. The critical temperature means the critical temperature of a gas is defined as the temperature above which it cannot be liquefied even at high pressure. The critical temperature of a gas is defined as the temperature above which it cannot be liquefied even at high pressure. So 33.19 in critical temperature of protium, 38.35 Kelvin in deuterium and 40.60 Kelvin in tritium. So liquid state protium in 33.19, in liquid state in deuterium 38.35 and liquid state in tritium 40.60. The enthalpy of dissociation enthalpy of dissociation kilojoule mole inverse. The bond dissociation energy in protium 435.9 kilojoule mole inverse, in deuterium 443.4 kilojoule mole inverse and tritium 446.9 kilojoule mole inverse. Okay students, the next one is Ortho and Para-H₂. Ortho and Para-H₂, right? So in a hydrogen atom, the nucleus has a spin. In a hydrogen atom, the nucleus has a spin. So one is the same direction, another one is the opposite directions. Right? So the hydrogen atom, the nucleus has a spin. When the molecular form of hydrogen, they join the same spin hydrogen. So nucleus combined to same spin hydrogen atom is called orthohydrogen. To combine the two hydrogen atom, one is a clockwise direction, another one is a opposite direction. So the opposite spin hydrogen atom contain nucleus combined to give para-hydrogen. Okay, the hydrogen nucleus. So both are same direction orthohydrogen. The hydrogen nucleus spin is opposite direction para-hydrogen. You right? In room temperature, the room temperature in normal hydrogen molecules. Normal hydrogen molecules consist of 75% of ortho form and 25% of para. So 75% of ortho form and 25% of para. Are you right? The isomeric form of ortho is converted into para process is very slow. Ortho to para or para to ortho process, conversion process is very slow. But in room temperature, so low temperature, in a low temperature, favor for ortho to para-H. Okay, so the ortho in ortho hydrogen is converted into para-hydrogen. Para-hydrogen in low temperature. In low temperature, favor for equilibrium in the para direction side. Para direction side. You right? The next, the conversion of para-hydrogen to ortho-hydrogen. The conversion of para-hydrogen to ortho-hydrogen. In ortho to para, low temperature. At low temperature, the ortho-hydrogen is converted into para-hydrogen. It's a slow process. Okay, so para-hydrogen to ortho-hydrogen. Para-hydrogen to ortho-hydrogen. So three methods. In a first method, the catalytically transfer. The catalytically transfer. So the para-hydrogen, the catalytically transfer using nickel, platinum or iron. Platinum or iron catalyst. Using platinum or iron catalyst, the para-hydrogen is converted into ortho-hydrogen. Para-hydrogen is converted into ortho-hydrogen. It's the first process, right? The catalytic transfer method. Catalytic transfer method using platinum or iron. In a second method, the passing electrical discharge. Electric discharge. The passing electric discharge in para-hydrogen. The para-hydrogen is converted into ortho-hydrogen. Ortho-hydrogen. In third method, para-hydrogen. In third method, para-hydrogen heating above 800 degrees Celsius. Heating above 800 degrees Celsius. Above 800 degrees Celsius and mixing with the paramagnetic molecules. The paramagnetic molecules. Mixing with the paramagnetic molecules like oxygen, O2, NO, NO2. They are paramagnetic molecules. Okay. In above 800 degrees Celsius and mixing with the paramagnetic molecules, oxygen or nitric oxide or nitrogen dioxide or nation hydrogen. Paramagnetic molecules are nation hydrogens. Okay. At above 800 degrees Celsius, the para-hydrogen is converted into ortho-hydrogen. Ortho-hydrogen. Okay. So the spin direction are also changed. The same direction ortho and different direction in para-hydrogens. Okay. So when ortho and para-hydrogen, chemical properties is similar. The chemical properties similar in ortho and para-hydrogen, but physical properties, some of the physical properties is differ. Some of the physical properties is differ in ortho and para-hydrogen. For example, melting point. 13.95 Kelvin. 13.95 Kelvin. The melting point of para-hydrogen 13.83 Kelvin. Are you right? So the chemical properties are also same in ortho and para-hydrogen, but some of the physical properties differ. For example, the melting point of ortho 13.95 Kelvin, 13.95 Kelvin, and para 13.83 Kelvin. The next, boiling point. The boiling point of ortho. The boiling point of ortho 20.39 Kelvin. 20.39 Kelvin. 20.39 Kelvin and para 20.26 Kelvin. 20.26 Kelvin. You right? The melting point of ortho 13.95 Kelvin and para 13.83 Kelvin. So ortho is higher melting point than para. Okay, the boiling point are also higher ortho than para. Right? 20.39, 20.26 Kelvin. The magnetic moment. The para, the nucleus spin in opposite direction. The magnetic moment is 0. The magnetic moment value is 0. So the nucleus spin in opposite direction. But in ortho, the spin in same direction. So the magnetic moment value is twice of that of proton. Twice that of proton. You right? Okay, students. The preparation of hydrogen. The preparation of hydrogen. The first method is electrolysis method. The high purity hydrogen, 99.9%. The high purity of hydrogen is obtained by the electrolysis method. Electrolysis method. The electrolysis contains water with traces amount of alkali or acids, or sodium hydroxide or potassium hydroxide. The electrolyte is sodium hydroxide or potassium hydroxide. Is using anode nickel rod. In anode, the iron rod is cathode. Okay, so anode is cathode. Anode and the cathode, the electricity passed through the electrolytic solution. Electrolytic solution at anode. The hydroxide ions, OH minus ions, is converted into water and oxygen. Loss of 2 electrons. Loss of 2 electrons at anode. Okay, so hydrogen, 2 hydrogen, loss of 2 electrons. 2 oxygen. So 2 oxygen. So of O2. So equation 1. In at anode. At cathode, the water molecule is, in a cathode, the water molecule is converted into hydroxide ion and hydrogen to absorb 2 electron. The loss of 2 electron in the anode and gain of 2 electron in cathode. So H2O, gain of 2 electron to convert to hydroxide ion and hydrogen. Right? So how many hydrogens? Okay, oxygen, 1 oxygen, hydrogen, 3. So half. Right? So H2O, loss of 2 electrons, so 2 electrons. Gain of 2 electrons, so 2 electron. So 2 electron, 2 electron. Hydrogen, 2, 2, 4. 4 hydrogen. Okay. So 2 H2O. 2 H2O, gain of 2 electron to convert to 2 OH minus and H2. Equation 2. In overall reaction. Yeah? In this process, in an overall reaction, the 2 OH minus ion cancel, 2 OH minus. Water, 1 mole of water is cancelled. 2 electron is cancelled. So water H2O, water is converted into oxygen and hydrogen. Okay, so 2 hydrogen, 1 oxygen. Okay, the electrolysis of water is converted into oxygen and hydrogen gas. Okay, so the electrolysis method is not economically for large scale production. Economically, not large scale productions. Okay, so in another one method, laboratory. So large scale preparation method, the hydrogen gas is easily prepared in this method. Okay, the laboratory preparation methods, the metal like zinc, tin, iron reacts with dilute acid to give hydrogen gas. The laboratory preparation apparatus. Okay, so taken in the pieces of granulated zinc taken in a wide mouth bottles. The bottle contain the 2 holes rubber cup. The bottle fitted in 2 holes rubber cup. In one end, the tissue funnel and which long stem. The long stem contain tissue funnel fitted in one side. In another side, delivery tube. Right? The another end of delivery tube is connected to a behave self-placed on the water contained in a trough. You write the dilute hydrochloric acid or sulfuric acid passed through the tissue funnel. Okay, the other end of funnel is dipped into the acids. The zinc reacts with the hydrochloric acid. The hydrogen gas is liberated. The liberated gas is passed through the delivery tube. Collect to the delivery tube. The download displacement of water. You write? Right. In this chemical reaction, the zinc reacts with the hydrochloric acid to give zinc chloride and hydrogen gas. Okay, so 2 chlorine, 2 hydrogen. The zinc reacts with the hydrochloric acid to give zinc chloride and hydrogen gas. Okay, the hydrogen gas is collected to the gas jar. Download displacement of water. Right? Okay, students. Thank you, students. We'll meet next class.